So are you able to see the screen? Hello?
Yes.
Okay, thank you very much. Last time I was talking about the Laplace transform, and today I'm going to talk about the inverse Laplace transform. As I show you last time, uh, the formula of the inverse Laplace transform, but we still have a problem. So because when we are performing some function with Laplace transform, we can end up finding a kind of complex problem in a frequency domain. So applying the table of the inverse Laplace transform will be uh, difficult, or we cannot find the correct answer. So that's why in the inverse Laplace transform, uh, we need to use another method that can help us to find a simple form of the Laplace transform that we can easily transform using the inverse Laplace transform. So that procedure will be to convert first the function that we have in a frequency domain. We have to convert it in a sum of partial fractions. And after we got the partial fraction, then we can apply the inverse Laplace transform using the Laplace transform tables. So this is what we are going to do basically today. And I hope we'll have another session at I think 1 o'clock. So hopefully we're gonna finish this inverse Laplace transform. So as you can see, when we're talking about the inverse Laplace transform, there is two things that I want to emphasize there, or that are very important, is what we call the zeros and the poles. Please, guys, put this in your mind. We call zeros when we have a function where we have a numerator and denominator. The zeros are the roots of the numerator of the function, and the poles, they are the roots of the denominator. So this you put just in a simple way. Zeros are the roots of the numerator, and poles, they are the root of the denominator of a function in a frequency domain. So these two elements are very important for us to be able to solve the partial fraction, especially the poles. They are playing a big role in finding the inverse Laplace transform. So to be able to solve this one, there is different cases that can be used to find the inverse Laplace transform, and all those cases, they depend on which type of poles you have. So which type of the root of the denominator that we have. So we are going to talk about first the first case, which is we have distant real poles. So as you know, we have real numbers and complex numbers. So here we are in the case where we have two real numbers, but they are distant, so they are not the same. It's not the same number. Like let's say we the root of a of the denominator can be 2 and 3, 1 and 2. So this is what we call the distant really poles. So this is the first case we are going to see. We are going to see. So first of all, what we can do is when we want to solve a problem, let me put this one to you. What is it? Okay, okay. If you're able to see it. Okay, let me go back to the slides. As you can see in the slide, they are showing us a function in a frequency domain where we have the numerator and the denominator. You can see on the denominator, they write s plus p1, s plus p2, and s plus pn, and so on. So, and they use they use different factors for the poles, for the denominator, and they create partial fraction, finding different coefficients that we can name K1, K2, and so on, Kn. So I want just, let me show if the whiteboard is ready. Okay, so let's say we have like a simple example. We can have a function where we have like we have f of s. Oh, let me try to write it now. Okay. Yeah. So we have there. We have there f. These things here. Okay, sorry for that. Let me try to put it in the right way. Please, can you mute your microphone? I don't know how these things are acting like today. Okay. 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 So let's do it now. Let's say we have a function which I call f. Okay. Let's say f of s, which is equal to, let's say, n of s, n of s over x power n plus x power n minus 1 plus, let's say, x something plus, and so on until we have a number there. So this is a function of this one. So when we have this type of function, we know that we should find the root of this function. So we'll have n root. So every single root, so the root of this one, they are called poles. So every single poles will help us to have different factors for our denominator. And once we have those factors, so we will be now able to solve to create our partial fraction. And after creating the partial fraction with the poles, then we're gonna be able now to solve the partial fraction. So let's see what we can do here. Okay, so let's now go back to the slides. Don't know. Okay. So here we have. So it means that this pole, these factors, they came for. It can be a simple equation, or it can be any equation that you have factorized to get different poles. So because this one we have like n poles, we can start from pole 1, pole 2, and pole 1, so we can create the k1 over this fixed phase factor, so which is made with s plus the first pole and the second one, and so on. So now when we got this one, what we will need is to find the value of k, and finding the value of k, we're gonna use, you can use identification methods, or here in control system, we have decided to use the AV side method formula. We assume that it's much easier to find the value of k. So, and the formula of the AV side formula is this one. We can say the ki, so I can be 1 to whatever, is equal to limit of s minus p I, s plus pi, f of s, and which is going to be equal to the limit of this one, which is the factor that the factor under the k we are looking for, times the function itself, then we find the limit of that. So these are basically what we are going to do here. So let's see if possible. Let's see if possible. After you find out this value of, you find the value of k1, k2, or until to kn, then you're going to be able now to use that function to put them back. So if you find the value of k from this formula, now you can replace your k on top of all these different partial fractions. So that's what we can have here. After replacing now, you're going to find that you will have simple function that you can easily apply the Laplace, the inverse Laplace transform, so you can get your answer. So this is how your answer is going to be look like. When you have k, so the inverse Laplace transform will always give you the numerator times e minus, according to what you're going to have as a denominator. So let's now try together to solve this problem. So I hope my my writing part will be able to, I'll use it better. Don't know why it's acting funny. And let's do this one. Let me try to go back there. What the problem? Y 5x plus. I think we solved already this problem before, but now we're going to use the inverse Laplace transform. So we have the given problem is okay. So we'll have 5 s plus 2 over s 5. Okay, over the bracket. Okay, okay. Say y s is equal to 5. These things here. Let me try to write differently because I can see this is giving me too much trouble. Okay, guys, let me try to use different method. We'll see if it's gonna work here. Okay, let's say I do have. Hey, now everything's not working. Yeah. Okay. Gosh, sorry guys. So what is happening today? Okay. Okay. Let's say 5 s plus 2 over s 5 s plus 4 to the brackets is equal to y is okay. So now when we have this problem, they ask us to find the inverse Laplace transform. So the first thing it will be to find this one, to transform this one or to convert it in partial fraction. So we know that to get the partial fraction, we need to find the roots of the denominator. So how can we find the root of the denominator? So we know that the root we're gonna equal to this denominator to 0. So we're gonna have s bracket 5 s plus 4. So the bracket is equal to 0. So we'll have the first root will be s is equal to 0, and the second one will be s is equal to, let's say, minus 4 over 5. Okay, so these are going to be our two roots. So, and then we can have now y of s is going to be equal to, the numerator is 5s plus 2 over, let's go now, s plus 0, and then we can have s plus 4 over 5. So this is going to be our new y. So then we can now transform it in partial fraction. You know, this is s plus p1, which is equal to 0, and s plus p2, which is equal to minus 4 over 5. So we can have now y s, which is going to be equal now to, ys will be equal to, say, we have k1 over s plus k2 over s plus 4 over 5. Okay. Guys, are we together? Hello, guys, are we together?
Yes.
Yeah. So
Yes, sir.
after we have found this partial fraction now, it's going to be the time to find now the value of k1 and k2. As I told you, k1 and k2 can be found using the Heaviside method. So let's use Heaviside method. We have k1, which is going to be equal to, we say the Heaviside method, let's go to the formula. So we're going to see it. Let's go. It's here. It's limit of s k1 for the first pole, and you multiply by the factors for under this value of k, and then this factor must be multiplied by the function. So this function here. So let's now try to solve it. So we'll have, let's go back there. So what you're gonna have is gonna be, so we'll have limit of s approaching 0, and gonna have the factor under k1 is s. So we're gonna have s times the function, which is 5s plus 2 over s, let's say 5s plus 4 plus 4, and you close it. Then we'll put this we'll put this one under brackets like this. So this is going to be equal to, okay, so limit this s and that s can cancel themselves. Then we're gonna have 0 there and 0 there, and then what we're gonna have is gonna be 2 over 4. It's gonna be 2 over 4, which is equal to 0.5. Okay, that is easy. Then we're gonna go for k2. Okay, K2 will be equal to limit of S approaching the second pole is minus 4/5. Then we're going to use this function, which is this factor, which is S plus, let's go, plus 4/5, then times the function, which is going to be, let's say, 5s plus 2 over s 5s plus 4. Close the bracket. So it's going to be equal to, okay, now solving this one, so we can find the LCD. They are going to be limits of s approaching minus 4/5. When you open the brackets, gonna have here, gonna have 5s plus 4 over 5, and on the other side we'll have 5s plus 2 over s 5s plus 4. So we got this one. Knowing that this one, they are the same, they can simplify them. Then we're gonna have here limits of s approaching minus 4/5. Then we can open in the bracket. So what are you going to have here? We'll have 5s plus 2 over 5s, because this one times the s is going to remain there, and close this one. Then the answer will be when we replace there. So we're gonna have 5 times minus 4 over 5 plus 2 over 5 times minus 4 over 5. I think that is it. Are we together, guys? Hello? Yeah, okay. So we can simplify this 5, can simplify that one 2, this one 2, and that one 2. So what we're gonna have here, we're gonna have minus 4 plus 2 over minus 4. Minus 4, yes. So this is going to be minus 4 plus 2 is going to be minus 2 over minus 4. That's going to be 2 over 4. You can put minus minus. It's going to be 0.5. Are we together? So now we have the value of K1, which is equal to 0.5. K2 is equal to 0.5. Now we can write our partial fraction, which is equal to y of s is equal to 0.5 over s over s plus 0 0.5 over s plus 4 over 5. As we have this one now, we can apply the inverse Laplace transform. Let me see if I can create another. What is this one? Is notes. No. Okay. How can I move to another page here? So, guys, can I delete this one? Or let me go just.
Yes.
Okay, you have a question?
Yes,
Okay, what's the question?
I'm lost from K2. I'm lost.
From K2.
Yes.
Okay. Do you understand how I find this one?
No, it's just one. This I don't understand. Name is approaches like negative 4/5.
Okay, you see, okay. I said, let me go back to the formula. Let me go back to the slides. Okay, you can see from the slide, I said to find the value of k, what you need is k1 will be the limit of ki, limit of s approaching pi. We use the factor that is under the k, multiply by f of s, which is our function. Then you find that limit here. Okay, so this is the same thing, but we have extended it so you can see properly. So we have our if we want to solve for k1 here, for this like k1, so this one will be k1 will be s approaching p1, s plus p1, right? Are we together? Then times f of s, so it's going to be limit of s times a approaching minus pi, s plus pi, then we can find this function. So this is what I did basically here. So okay, we had our for k1, we use limit of s, our first pole, which was equal to 0, limit of s approaching 0, then we use this s, the s which is here, this s, the one who's down there, this s, we multiply it by our y of s, which is s times this times s plus 4. So this is what we did basically for this first one. So when we multiply, we can simplify this to s, then we can replace the 0. 0 can replace s there, then we're going to have 2 over 4. So the second case also was the same. But here we know that our poles, when we solve our poles, s here was minus, or let me just write it in this way. So this is going to be easy to get it. Yeah, let's say this one is, okay, let me find the pen there. Okay, let's say this one is P1. This is equal to S. You got 0, then P2 is equal to, so let me this technology here. We need to get used to it, but we get used to it, so it's not a big problem. Okay, so let's say this one is P1 and this one is P2. Okay, so we have this minus 4 and over 5, and this is 0. So that's why here now we're going to use P2. So we know that the factor that is under K2 is S plus 4 over 5, which is S plus P2. So we're going to have you open the brackets, we're going to have S plus 4 over 5 Then we do times y of s as we did for the first one. So now, you know, this one is a fraction. So we can first find the LCD, the lower common denominator. So this is what I did here. I find the lower common denominator of this factor. Then after I find this factor, I can see in my equation that on this first factor, I have 5 plus 4 on the numerator. And on the second one, I have plus 5 plus 4 on the denominator. So I can simplify these two because this one is on numerator and the denominator can simplify. So I will remain with, let me write it even there, I will remain with 5. Okay, let me do it in this way. Okay, doing it this way, I got this one. Okay, so now let me write it even in red. So I can have there 1 over 5. Okay, this one gonna give me 1 over 5. Then that will be times 5. 5. Oh, let me. Okay. Okay. That's gonna be over 5 s plus 2 over s. Okay, because this one, when you cancel this one here and you cancel that one, here you're gonna have 1, and there you're gonna have 1 times this s that was already there. So this is s. This is s. It's not 5. This is s times that. This s there. So you're gonna have. Let me just put it clean. Yes, in a good way. Okay. Okay. So that one is s. So it's gonna be times this s here. So this gonna be f this one. So then gonna 1 times 5 plus 2 is going to give you 5 plus 2, and 5 times s is going to give you 5s. Then now I'm going to solve the limit of this one. Then I will replace this one wherever there is s. So replacing this one where there is s, so I will have minus 4 over 5 where there was s. Because there is s there, there is s there. Then I replace, I can simplify this one because I will have 5 times 4 over 5. So I can simplify already this 5 and 5. Then also I will have 5 times minus 4 over 5. I can simplify the 5. So I will remain with minus 4 plus 2 over minus 4. Then this one, minus 4 plus 2 is equal to minus 2 over minus 4, it is 0.5. Did you get it now?
Yes.
Okay, thank you. So now we can now, let's see if there is a way. So can I delete this? Okay, anyway.
Yes.
Yeah, there is, we had it already in the slide. So once I delete this one, okay, then I will have, okay, good. So now I'm going to have, here we have y s, which gonna be equal to k1. Oh, sorry, I've already found the value of k. We have already found the value of k, so let's go back there then. It's gonna be equal to 0.5 over s as 0.5 over s plus 4 over 5. So now what's remaining, we have our partial fraction. We have found the value of k1 and k2. Now we can just apply the inverse Laplace transform to our our problem. Minus 1. And we also have there the inverse Laplace transform. Let me put it even there. Sorry for that. Minus 1. So now we know that from the table we can find out the inverse Laplace transform of our problem. Let's see if I can go to the table, or you can check it yourself because you have the table. Okay, so I'm gonna have something like y of t, which is equal to be equal to this one. Gonna give you 0.5, okay, plus 0.5. So when we go back here, let me show you something. They say the answer will be for S plus P1 here, gonna be K1 times E P1T. So we know that P1 is equal to 0. So it's gonna be, this gonna be 1. So that's why we have 0.5. And the second one will be K2 times E minus P, the pole we have there, times the time. So this is gonna be now times, let's go here, times E. Okay. So what is the pole we have in there? The pole is minus 4/5 times T. So this is our answer. So if you want, you can even divide this by 5. You can find something. So this is exactly what we can do as a partial fraction. But this solution can also be easily found using MATLAB. I think tomorrow you must make sure that you have your MATLAB ready. I was told that Monday, 1st of November, there is election, so they won't be lab. So I would like to introduce tomorrow MATLAB online. That will be tomorrow, I think, in the morning at 9:15. So we're gonna introduce MATLAB tomorrow at 9:15. So be ready with your MATLAB. I'm going to introduce you tomorrow. So I think next week, Wednesday, we're gonna meet in the lab. And for the evening will be on Thursday evening. Okay. So this is how you can find the partial fraction. I will show you tomorrow how you can solve this problem in MATLAB. So let's now take this example here. We have an example. Let's see. I think we must have an example in our note here. Okay, which is f of s is equal to 2/s plus 1 plus 2. Okay, so we have y. Okay, let me delete this one, then we can start afresh with a new one. Okay, good. So we have this one. So having that, say y, we call it y of s. Y of s is equal to 2/s plus 1 and close there, s plus 2. So we know we have here, this is our denominator. Please, how many poles do I have here? Guys, how many poles do I have here? Sorry,
2.
how many? No. How many?
2.
3 poles. This is a third order equation because we have s times this one times that is going to be x cube. So I will have my first pole will be P1. So let's say P1 is going to be equal to S is equal to 0. This is going to be P1. And P2 is going to be S plus 1 is equal to 0. Then S is going to be minus 1. And P3 is going to be S plus 2 is equal to 0. S is going to be minus 2. So I have three poles. I have 0, minus 1, and minus 2. So which is equal to P1, P2, and that one is P3. Okay, so this is what we have there. Then what we need now is to write our partial fraction, which gonna be y s, which gonna be equal to what? Gonna be equal to we can change now. We can have, because we have that form already, we can say k1 over s plus k2 over s plus 1 plus k3 over s plus 2. So we have this partial fraction. Now we have to use Heaviside method to find k1, k2, and k3. So let's go for k1. K1 will be going equal to limit okay, this is going to be limit of limit s approaching 0, and we're gonna have, can open this square bracket, s times 2 over s plus s factor s plus 1, then s plus 2, close the brackets. So like this, this s and that s can cancel themselves. So you're gonna have, when we put 0 there, it's going to give us, so 0 plus 1 is equal to 1. 0 plus 2, it's gonna be, we're gonna have 1 there, times 2, it's gonna be 2. So our first pole will be equal to 2 over 2. It's gonna be 2 over 2. This is gonna be equal to 1. Okay. Now let's go for K2. So K2 is gonna be limit of s approaching minus 1. Then we open the brackets. We know the factor which was s plus 1. We're gonna have s plus 1, close the brackets, then times 2 over s, then we're gonna have open the bracket, s plus 1, s plus 2 is gonna be equal to, let me write it, extend it, 2 over this one and that one can cancel themselves, s times s plus 2. Knowing that our s is equal to minus 1, so we'll have 2 over minus 1, open s. Okay, let's, okay, good, okay. We'll have here minus 1 times minus 1 plus 2. So it's equal to what? So this one is going to give us 1. It's going to be minus 1 times 1 is going to give us minus 1. So 2 over minus 1 is going to give you minus 2. This is what we have there. Then we can have K2, which is going to be equal to limit of S approaching minus 2. When you open the bracket, we have the factor under K3. Sorry, this is K3. Okay. Go there. We're gonna have K3. So what we have there is gonna be, open the bracket, S plus 2, because this is the one under there, and we 2 times S, we open the bracket, S plus 1 times S plus 2, which is 1 is going to equal to, so this one can cancel with that one. So we're gonna have 2 over, let me first delete this one, I'll just showing you. Okay, so we're gonna have here, gonna have 2 over S plus 1, and this is gonna be limits approaching minus 2. So this is gonna be here. There's limit here. I think there is limit there. And let me also put this one. Okay, at least you can see that there is a limit there. Sorry, and this one is going to be equal to what? Let's replace. Now we're gonna have 2. Here we're gonna have minus 2 times minus plus 1 minus 2 plus 1. So this is gonna be minus 2. This one gonna be minus 1. Minus 1 plus minus 2 is gonna give us 2. 2 over 2, so it's going to give us 1. Okay, so we know that now we have our y of s, which is going to be equal to k1 is equal to 1 over s plus k2, which is equal to minus 2. So this one will be minus, so f minus 2 over s plus 1, s plus 1, then plus 1 over s plus 2. This become now easy if we apply here the L inverse, and then we apply again L inverse there. So we have this gonna be 1 minus 2, which is the k1, times e, and this one will be minus t, I think so, minus t, then we're gonna have plus, this one is 1, it's gonna be e minus 2t. Good. So this is what we're gonna have. If you want, you can add the units, or you can add or not, depend on you. But because this one considered is equal to 1, so when I have 1 minus e2 minus that one minus that one. So guys, are we together?
Yes, sir.
Okay, thanks. So after we finding this one now, we can see the next case, I think, which is the case of complex roots. We only have 5 minutes, so I will just introduce it, but I won't give it, because this one is going to take quite long to explain. So for the case of the complex roots, we are using the same example, the same formula as for the first one. So you find first the poles, but we know that with a complex root, we have the presence of G. So you find first the poles. After you find the poles, so you will have, it can be, all of them can be imaginary poles, it can be uh, complex imaginary with, normally consider imaginary with real parts. So you find first the roots. After you find the root, then you can find now the value of K1, K2 using the Heaviside method. And after you use the Heaviside methods, then you can find the inverse Laplace transform. So after you find the inverse Laplace transform, it can happen that by solving, you can solve finding this type of identity. You will see, and when you are solving, it will be better so you can fight to find this form of identity. So we know that these identities can give you, like, when you have this form here, you have equal to 2 cos phi, and this is giving you 2g sine phi. So this is the two identities that we're going to use to replace when we solving our solution in time domain. So maybe I can try. Okay, so I think we will solve this one later. We'll solve this problem later. Um, but I want just to remind you something very simple that you might all know. It's a quadratic equation that is very important in this case. Let's say, oh, this one doesn't work now. Okay, quadratic equation. So let's go there. Let's go there. Okay. Let's say you have, okay, quadratic equation. This seems like a joke, but most of you have forgotten. S plus 3s plus 2, which is the quadratic equation, is equal to 0. So to find the root of this equation, S1 and S2 going to be equal to minus B plus minus root square of delta, okay, over 2a. Okay, so where here there is a, this is can call as that. Let me just write it in this way here. Let me remove this value here. Let's say we have here a plus bs plus c. This is how you can solve. So this here you're gonna have minus b plus root square of delta over 2a. You're gonna have minus b minus root square of delta over 2a. This is very important. Don't forget this formula, where delta is equal to b square, or is equal to b square minus 4ac. Okay, when you have this example, this one I will give to you so you can solve it. Let's say we have s square plus 5s plus 4 is equal to 0. So this is 1. Please try to solve these things before we will come back at 1. So s square plus 3s plus let's say 2 is equal to 0. and this one 4 is gonna be, this one is gonna be number 3. Please guys, you can try to solve this one before we come back at 1. Is it 1 or 2? 1 is the next class. A square plus 6s plus 9 is equal to 0. So you can try to solve these three problem, find the solution. Okay. Okay, guys.
Yes.
Okay. So I think, thank you very much. This class, I'm ending this class here by here. Let me see what is happening. Okay. I'm going to end this class by here now. So I will post the video on Blackboard, and also you can find them on MS Team. Then after, we will meet again later. Let me now stop the recording. Is
Hello,
there any
sir.
question? Yes?
Yeah, can you please slightly show us the examples that you want us to do? The last three you wrote.
Yeah, okay. Okay, this one. S squared plus 5s plus 4, s squared plus 3s plus 2, and s squared plus 6s plus 9.
Thank you.
Okay, you're welcome. Is there any other question? Yeah, sorry for the delay. As I'm set now, I think the next session we will start it on time. We won't have any delay unless something happens. Thank you.